Welcome to Unit 1.9 Chemical Analysis. In this video we're going to try and go through the whole topic of chemical analysis. Now most of this topic you have covered before in junior school. There's a bit at the start and a bit at the end that you haven't covered before, but that bit in between you've covered in junior school. So let me run you through the topic. So we're going to look first of all at types of substances, and essentially we can classify substances, and that's a very general vague term, but we can classify them into pure and impure substances. We're also going to look at a special type of mixture called a formulation. We're going to look at what that is, how you define it, and what it can be used for. We're then going to look at some separating techniques for how we separate mixtures, and this is what you have covered before in your junior science. So we're going to look at things like filtration, evaporation, crystallization, distillation, fractional distillation, separating funnel, and chromatography. And all or most of these you have met before. And then the final part of the topic is what we call our chemical analysis. And in that we are going to look at flame tests, which is how we identify the metal ion present in a salt. And we're going to look at the test for water. So that's an overview of where we're going with this topic, and let's get stuck in. So on page 1 and 2 you have your specification for this topic, and again that allows you to use this as a checklist when you're revising for this topic. Do you know all the different areas of the topic? At the bottom of page 2 you have a definitions page, which I would advise learning now and learning these definitions off by heart. Sometimes they can randomly throw these in, which I think is a bit of a waste because there's so much content to cover in the exam. But the one that they ask from time to time is, what is the definition of an element? And loads of people just leave it out because they can't think of a definition as such. But this is something you've talked about from junior school as well. An element is essentially what is on the periodic table. Your periodic table is called the periodic table of elements. It's all the elements known at this time. And what an element is a substance that is made up of only one type of atom. So if you think of sodium in the periodic table, sodium is only made up of sodium atoms. It doesn't have any magnesium atoms or any carbon atoms in it. Sodium is just pure sodium atoms. So an element is a substance that is made up of only one type of atom. A compound is a substance that is made up of two or more different elements that are, and here's the important part, chemically combined. Okay, so if we had, for example, say two hydrogen atoms that were bonded to an oxygen atom, that would have the formula H2O, and that is a compound because those hydrogen atoms and those oxygen atoms are chemically combined together. So that is a compound, two or more different elements that are chemically combined. But in terms of a mixture is a substance that contains two or more substances. They can be elements or compounds, or elements and compounds, but they're mixed together. They're not chemically combined. So let's stick with hydrogen and oxygen. Well, we know that hydrogen and oxygen are both diatomic. So if we were to draw them in here, we would need a diatomic hydrogen molecule and a diatomic oxygen molecule. This time we have the same elements in this substance. We have hydrogen and we have oxygen, but this time they're a mixture because they are not chemically combined. So just be really careful when you're identifying types of substances. Does it contain only one type of atom? Well, that makes it an element, even if you have more than one of the atom chemically joined, like we've seen here with our mixture. So if we looked at, we could have a single atom for our element, or we could have a diatomic molecule, but because they're the same type of atom, it's still an element. So it's a substance that is made up of only one type of atom. And for our definition for compound, it's a substance that is made up of two or more different elements that are chemically combined. So it can't fall into that category of an element because we have two or more different elements. And then a mixture is a substance that contains two or more substances, elements or compounds, or a mixture of both, that are mixed together but they're not chemically combined. We will make quite a few other definitions, and there's other definitions that are mentioned in your specification on the front page, on page 1, but we will meet those throughout the topic. So over onto page 3 then, let's talk about this idea of pure substances. So we said the first section of our topic looks at pure and impure substances. So in terms of chemistry, a pure substance is a single element or compound that is not mixed with any other substance. So it can be an element or a compound, but it just must not be mixed with any other substance. So we can have an element, we can have a compound, but we can't have a mixture. That's essentially it. So let's look at pure water, for example. So when we talk about pure water, in our everyday terms, we might be referring to it as water that's clean or water that we might buy in the shop. But actually the technical chemistry definition of what pure water is water that contains only water molecules. So the only molecule present in that liquid is water molecules. So you can see them here in this first diagram where we have pure water, where the only thing present is water molecules only. But in reality, even the water that they sell in the shop is not pure water. Yes, it's clean, yes, it's safe to drink, but it is not pure water because it has lots of different ions dissolved into it, lots of different salts that have dissolved into the water and broken off into their ions. In fact, if you look at your label on your water bottle, you might see something like this, and you have a list of ions that are present in your water. Now some water bottles will have the formula of the ion there as well. So we can see that we have 48 milligrams per litre of calcium ions. That will be Ca2 plus ions. And we have 25 milligrams per litre of sodium ions, which will be Na plus. 2 milligrams per litre of potassium ions. We've got magnesium ions, bicarbonate ions, chloride ions, nitrate ions, and sulfate ions as well. So you can see all of these ions are mixed in with the water. They're all dissolved in the water, which means they're mixed amongst the water molecules as well. And so therefore, this mineral water that we buy in the shop is not pure water because it has other ions dissolved in it, or other elements or other compounds. It doesn't matter. It's called impure substance if it has any other element, compound, ion, or salt dissolved within it or mixed in with it. So you can see here I've coloured in my water molecules blue, and I've coloured all my other ions in a different colour, so you can see how many different coloured ions there is there, how many different ions there is present within that water mixture, and therefore we call this impure. So our first diagram, it is pure water. Why? Because it only has water molecules in it. Whereas our mineral water is what we would call impure. Why? Because it is a mixture of water molecules and dissolved salts. There are other substances present, not just water molecules. So this is impure. So in determining whether a substance is pure or impure, in terms of a molecule diagram or an atomic diagram, what you're looking for is something that contains one thing only. So going back to this definition, a pure substance is a single element or compound that is not mixed with any other substance. So it's one thing only. So the next part of the topic, you need to be able to tell, well, how do you tell the difference between a pure and an impure substance? So if you had water, or if you had some sort of solid, some sort of compound, and you were asked to determine is it pure or not, well, what would you do? But before we look at that, we need to look at two definitions. We need to look at the definition of melting point and of boiling point. And you probably think, well, I know what this is, but again, this is something that they can ask, and it can be a 2-mark question, but loads of people lose out marks because they might say the melting point is the point at which something melts. Well, no, you haven't really given me what that actually means. You've just rearranged the word. Melting point is the point at which something melts. No, that's not going to get you the mark. Well, what is the melting point? Let's think of water again. What is the melting point of water? Well, the melting point of water is 0 degrees C. So what is that? What is 0 degrees C? Well, that's a temperature. So part of my definition of melting point needs to be the temperature. So that's the start of my definition, the temperature. But what happens at that temperature? Well, at that temperature, we see that melting happens. But what is melting? What does melting mean? Well, melting is when a solid is changed into a liquid. So that needs to go in our definition. So not the temperature at which it melts, but the temperature at which a solid is changed into a liquid. So you can see how we've made a much better definition here. Rather than saying the point at which something melts, instead of saying point, we're saying the temperature at which. And then instead of saying melts, we need to explain what does melting actually mean. Well, melting is the change of state from solid into a liquid. So for water, 0 degrees C is the temperature at which the solid form of water, i.e. ice, changes into the liquid form of water. So 0 degrees C is the temperature at which ice changes into water. Well, what about the boiling point then? Well, the boiling point of water is 100 degrees C. You should be familiar with that. But what does that describe? So again, you could just say it's the point at which it boils, but you wouldn't get any marks for that. What is 100 degrees C? It's a temperature. So the start of our definition says the temperature at which what happens? Well, boiling, what is that? The change of state. That's the change of state from liquid to gas. So instead of the definition, where the definition of melting point is the temperature at which a solid changes into a liquid, boiling point is the temperature at which a liquid changes into a gas. So if we use the example of water here, 100 degrees C is the temperature at which water changes into steam. So melting point is the temperature at which a solid changes into a liquid. And if we think of water as our example, that is ice turning into water. The boiling point of water is 100 degrees C, and that's the temperature at which water changes into steam. So those definitions you need to be clear on. They're very straightforward, but it's just about getting them right and actually explaining what does melting point and boiling point actually mean. Those could be a 2-mark question. So over on the next page, we start to get a picture of, well, what does this melting point and boiling point matter in terms of purity? So what we need to think about first of all is what happens when a substance is undergoing this process of a change of state. So this graph again represents water, and you can see that because we've got melting happening at this part of the graph here. And you can see that that's at 0 degrees C. So melting is happening at 0 degrees C. And then if we look at our boiling stage of the graph, that's this horizontal line here. And you can see that that is happening at 100 degrees C. So this graph is representing water, but it could be representing any form of pure substance. So what we can see here at the start of our graph, we start here at minus 40 degrees C. And between minus 40 degrees C and 0 degrees C, water is a solid. It is ice. And you can see here that as we go up the graph, our substance is absorbing heat and the temperature is rising. Once it gets to 0 degrees C, then the ice starts to melt. So the solid form starts to melt into a liquid. But what you can see is that it's absorbing more heat. So we're going further along our x-axis, which means we're absorbing more heat, but the temperature is not rising. So what is happening at that point where more heat is being absorbed, but the temperature is not rising? During that stage, melting is happening. So what you can see is that during the process of melting or boiling, the temperature of the substance doesn't change despite the fact that heat energy is still being absorbed. So we can see from the x-axis, the fact that it's going further along the x-axis, that it's absorbing heat, but the temperature is not changing during that change of state process. This point here at the end of the horizontal line will be once all of the solid has turned into a liquid. And once all of the solid has turned into a liquid, what we can see then is that the temperature of the substance starts to rise again. So we're absorbing more heat because we're going further along the x-axis, we're going further right. But we can also see that the temperature is rising because we're going up the y-axis as well. We're going further up the graph as well. So the temperature rises and rises and rises until it reaches this temperature here, 100 degrees C. What happens at 100 degrees C? Well, our water starts to boil. So our water starts to boil and we can see that heat is being absorbed, but the temperature is not rising. So we can see that it's staying steady at 100 degrees C. So even though it's absorbing more heat in order to change from a liquid into a gas, the temperature is not rising. So again, we see this during the process of boiling this time, the temperature of the substance does not change, despite the fact that heat energy is still being absorbed. So heat is being absorbed, our water is changing into steam, boiling is happening. And at this point here, what has happened? Well, at this point, all of the liquid has turned into a gas. And after that point, you can see the temperature starts to rise again. So as the molecules are absorbing more heat, the temperature will start to rise again. The key thing you want to see from this graph is that during change of state, the temperature of the substance does not change. So even though the substance is absorbing more heat to get all of the molecules to change from either a solid to a liquid or a liquid to a gas, the temperature is not rising until all of the molecules have turned from either a solid into a liquid or a liquid into a gas. So how does this idea of melting point and boiling point relate to the purity of a substance? Well, pure substances tend to have a sharp, specific melting and boiling point. Sharp and specific. What we mean by that is that they will start to melt at, say, for example, 0 degrees C. So that's the sharp part of it, and it's specific. So if that substance is pure, it will match the exact melting point on record for that particular substance. So it's sharp and it is specific. It won't melt over a range of temperatures, like from -2 until 3 degrees C. It will be sharp right at 0 degrees C, and it will be specific to the particular substance that it is. And the same is said for the boiling point as well. So for example, pure water will have a melting point of 0 degrees C and a boiling point of exactly 100 degrees C. Those melting points and boiling points are sharp and they're specific. So you really, really need to learn those two words. Pure substances have sharp, specific melting points. How does it change if the substance is impure? Well, impure substances do not have sharp melting points or boiling points. Instead, they melt or boil over a range of temperatures. So they could melt over a temperature range of 210 to 214, where the pure substance melts at exactly 214 degrees C. So you can see they're melting over a range of temperatures rather than at one sharp, specific melting or boiling point. So if we relate this to the graph above, instead of the temperature remaining constant while it is melting, the temperature will actually be going up a little bit during that melting process, which is how we could tell that the substance is impure. So how we identify something as an impure substance is that it will melt or boil over a range of temperatures. But how does that range of temperatures differ from the exact specific melting or boiling point of the pure substance? Well, if we're talking about melting points, impure substances tend to have a lower melting point, but a higher boiling point. So if we're talking about the melting point will be slightly lower than the expected value. But if we're talking about the boiling point, and this is an impure substance, it will have a slightly higher boiling point than the pure substance. And the more impure it is, in other words, the greater the amount of other substances present in the substance, the further away the melting point and boiling point will be from the true melting point or boiling point. So say, for example, we were talking about that substance that has a melting point of 214 degrees C. Well, if it had then a melting point of 210 degrees C, we can see that it's impure because it's a lower melting point than expected. But if it was 206 degrees C, we can see that it's even more impure because it's even lower than that expected melting point. So again, think of pure substances. The two words you want to be thinking of are sharp and specific. So pure substances have a sharp and specific melting point and boiling point. Impure substances will melt or boil over a range of temperatures, and the melting point that we see will tend to be lower. So it will have a lower melting point than the pure substance, and it will have a higher boiling point. It will have a higher boiling point than the pure substance. So you could be asked in an exam how to test a substance to see whether it is pure, and this has been a question a couple of times since the specification changed a couple of years ago, so it is quite a common question to be asked, so make sure that you're familiar with this. So the first thing you need to do is look out into the question to see whether your substance is a solid or whether it is a liquid, because that determines what you do. So essentially, just like testing for a gas like hydrogen or carbon dioxide, hydrogen where you apply a lit splint and a popping sound will result, you're describing what do you do and what do you see if that gas is hydrogen, what do you observe if that gas is hydrogen. So again, we need to say what do we do first of all, and then what can we tell from our results. So first of all, you need to determine from the question, is your substance in question a solid or is it a liquid? So if it's a solid, what are we going to do? Well, if it's a solid, we're going to determine its melting point. There's no point determining its boiling point, because in order to determine its boiling point, we need to convert it into a liquid first and then change it into a gas. So if it's a solid, we need to find its melting point. So that's the first thing. That is the what do we do? So we've done that. What do we do? And then what can we tell from our results? Well, we know that a pure substance has a sharp and specific melting point, but that an impure substance will melt over a range of temperatures. So if it has a sharp specific melting point that matches the known value for the substance, then it is pure. So that comes back to our properties of the melting points of pure substances. So if it has a sharp specific melting point that matches the known value for the substance, then it is pure. But if, however, when we are determining its melting point, we find that it melts over a range of temperatures, so say, for example, we're observing it and it starts to melt at 210 degrees C, but then it finishes melting at 214 degrees C, then we know that it is melting over a range of temperatures, and we know that it is impure. So if it melts over a range of temperatures, and how is the melting point changed? If it's an impure substance, the melting point will be lower. So if it melts over a range of temperatures and has a lower melting point than the known value, then it is impure. So that's really important. If we're determining the purity of a solid substance, the first thing we need to do is find its melting point. That's what we do. And the second thing is, what can we tell from our results? If it has a sharp specific melting point that matches the known value for the substance, then it's pure. But if, however, it melts over a range of temperatures and it has a lower melting point than the known value, then it is impure. So that is, what can we tell from the results? That's our second part. However, what we do if the substance is a liquid is slightly different. So if our substance is a liquid, then it is slightly different. Instead of finding the melting point, what could we do instead? So there's no point finding the melting point because it already is melted. It's already a liquid, so there's no point finding its melting point. So if it's a liquid, what would we do? And what could we tell from our results? What I'd like you to do is pause the video and try and fill in this little section yourself. So these 3 bullet points. What do we do? And then what will we see from our results to tell whether it's pure or impure? So try and fill this in yourself now. Pause the video and then play it again when you're ready to check your answer. Okay, so to check your answer, if the substance is a liquid, the first thing we need to do is find its boiling point. So first thing, what do? We find its boiling point. So that's the first thing marked off. And then what can we tell from our results, the second part? Well, if it has a sharp, specific boiling point that matches the known value for the substance, then it is pure. Okay, so again, there's your two key words again. If it has a sharp, specific boiling point that matches the known value for the substance, then it is pure. However, if it boils over a range of temperatures and has a higher boiling point than the known value, then it is impure. So you've got to be careful with that one. Remember, with melting point, it has a lower than expected value. With boiling point, it has a higher than expected boiling point. So again, you can see we've discussed what can we tell from our results. Now, normally in the exam, you'll be given, how do you prove that this substance is pure? So what you would say is, say for example, it's a solid, you would say, find its melting point, and it should have a sharp, specific melting point that matches the known value for the substance. Or if they say, how would you prove that this solid is impure? You would say, what do you do? Find its melting point, and then what can we tell from our results? If it's an impure substance and they've told you that, then you should say, well, it will melt over a range of temperatures that is lower than the melting point known for that substance, then it is impure. And if it was a liquid, then what you would be saying is find its boiling point. And if it boils over a range of temperatures and the boiling point is higher than the known value, then it is impure. So look out for what they specify in the question. Have they specified it's a solid or a liquid? Have they specified is it pure or impure? And go from there. And the last thing we need to look at in terms of substances, we've looked at pure and impure substances. The last thing we need to look at is something called formulations, and then we'll move on to separating mixtures. So a formulation, by definition, is a mixture that has been designed as a useful product. And if it's going to be a useful product, and if it's a mixture, it's going to need exact, carefully measured out quantities, and we'll come back to that in a second. So how does this work? Well, the properties of a mixture are such that when you mix substances together and not chemically combine them, the mixture possesses the properties of all the substances that make it up. And there is an S that is missing at the end of possesses, so you can add that in. So when we mix different substances together, all of their properties are present within the mixture. So you would have looked at this back in year 9 when you looked at your iron and sulphur practical. When you mix iron and sulphur together, the iron is still magnetic, so you can still separate the iron out by using a magnet. But when you heat it up and the iron and the sulphur react together and chemically combine, then the iron is no longer magnetic within the compound. The properties have changed. But within a mixture, because they are just mixed together and not chemically combined, then the properties of the individual components of your mixture are still shown in the mixture. So formulations are formed when several different substances are mixed together in exact, carefully measured quantities. We're talking even about things like medicines here, so they have to be in exact, carefully measured quantities if they want to have the desired properties that the manufacturer wants. So it's really important that you learn that definition and those properties as such, because sometimes this can be a 3-mark question. They may give you an example of a formulation and they might ask, why could this be defined as a formulation? And you would say, well, there's a mixture that's been designed for a useful product, and the different substances have been mixed together in exact, carefully measured quantities to ensure the resulting mixture has required properties for its use. So it's really, really important that you know all of that information at the top of this page. So let me introduce you to a couple of examples of a formulation so you can start to see, well, what does this actually mean? So the first example we'll look at is an alloy. This definition we learned back in our bonding and structures topic. So an alloy is a mixture of elements, at least one of which is a metal. So you might have a few different metals mixed together but not chemically combined. Or you may have metals and non-metals mixed together, which is still an alloy because there's at least one metal present. But remember, they're mixed together, not chemically combined. So each different alloy that we use, alloys have loads of different uses. And each alloy is a formulation made by mixing measured quantities to ensure the alloy has specific properties required for its use. Because remember, each of the substances present in the mixture will bring its properties with it. So if you have an alloy of iron and chromium, the properties of iron will be in the mixture and the properties of chromium will be in the mixture, and you might want a specific quantity of each to make sure that your alloy, your formulation, has that specific use. Another example you can think of is steel, which is a mixture of iron and carbon, and it's used in construction materials. So it's so important that we get the quantities right. If we have too much carbon, then it can be too brittle. We want the strength of the iron there. So we need to make sure that if it's being used for construction materials, perhaps bridges or big buildings that is going to support a lot of different people working in that building, then it must be strong enough. It must be in the exact quantities. So it's really important that it's a formulation, that the quantities of iron and carbon have been carefully measured out. Formulations are also used in medicines. So for example, the likes of paracetamol, it can be sold to you in the form of a capsule or a tablet, or even like a round tablet that has a little bit more easy to swallow. Or you can even get medicines in liquid forms, and those are also formulations. So the likes of Calpol is a liquid form of paracetamol that is quite often given to children because it's easier to swallow. So that mixture of your active ingredient, of your drug, along with cornstarch to bind the tablet together, and even a lubricant to make it easier to swallow. All of those things are mixed together in carefully measured out quantities to make sure that the drug is still doing what it needs to do. So an example of that is Calpol, which is a liquid form of paracetamol. It's a formulation of paracetamol and liquid flavourings. And then finally, this is something you looked at last year in year 10, the use of fertilisers. So the three main elements in fertilisers to assist plant growth are nitrogen, phosphorus and potassium. Can you remember what you called those types of fertilisers? They were called NPK fertilisers. So N for nitrogen, P for phosphorus and K for potassium. And depending on what your plant needs, you might have a higher percentage of nitrogen in one certain fertiliser, or depending on what your plant needs, you might have a higher percentage of potassium in your fertiliser. So what you can see there is that we have different measured out quantities of nitrogen, phosphorus and potassium, different ratios of nitrogen, phosphorus and potassium, depending on what the plant needs, whether it needs to support protein formation for growth, whether it needs healthy leaves or healthy roots. That's what your nitrogen, phosphorus and potassium are for. So depending on what your plant needs, you will have different measured out quantities of nitrogen, phosphorus and potassium. And so that is what we call a formulation, because it's a mixture that is designed for a specific purpose, a specific use, and it has exact measured out quantities that will make sure that the mixture has properties that are suitable for its use. So again, those are three examples of formulations, but the key thing that you know is these definitions and properties of formulations. That formulations are mixtures designed for a useful product, and that they're formed when several different substances are mixed together in exact, carefully measured quantities, so that the resulting mixture has the required properties for its use.